Hey there. In this video, we're going to be talking about dealing with differential equations that involve impulses. So these are just sudden spikes of force, like you'd have if you hit a ball with a bat, right? Just all of a sudden, wham! Just a sudden impulse of force there, and we want to see how we can handle this in a differential equation. And in particular, we're going to be using Laplace transforms to handle this. So this is a continuation of our videos on Laplace transforms. And the way we're going to treat this is by using something called the Dirac delta function. The Dirac delta function is named after a famous physicist, Paul Dirac, who is known for discovering antimatter, among many other things. He got the Nobel Prize with Schrödinger as well. So let's take a look at how all of this works. Well, the Dirac delta function is denoted by the Greek letter delta. Right? So the way to express it is like this. And the way we think about this is as if it represents an infinite spike at zero. Okay, so in this sense, it is not a real function as we usually define them. All right, so it's infinity when t equals 0, and it's 0 elsewhere. Okay, so it's just a spike at 0. Now, this can be made mathematically rigorous, and the way we talk about this mathematically, really we have to go to the theory of distributions, and that's beyond these videos. But you can kind of think about it as the limit of a sequence of functions. Okay, so one thing we can think about is a bump function. Okay, so I'm going to denote this bump function with a parameter epsilon. And this is going to be a bump function. It's going to look like a little bump. And the properties that it has is that the area under the bump is equal to 1. It's a positive function. And the width is given by epsilon. Okay, so this is a positive bump function with width given by epsilon. So one very famous bump function that people study is the normal distribution function. It has this property, and I forgot to mention I should write here the area under the curve is equal to 1. And the normal distribution satisfies exactly that. It's a probability distribution, so that was what makes the area have to be equal to 1. Those represent probabilities. And the normal distribution, this is a rather lousy picture of it. I'll show you a better one on the computer. It is given by a couple parameters. One is the mean, and then the other one is the standard deviation. The standard deviation roughly tells you how wide it is. This is what we're treating as our epsilon here. And so by making the epsilon small, making the standard deviation small, this bump gets very tight. But since the area has to stay equal to 1, it has to get very tall. And so it approaches a spike at the mean. And so it approaches what we think of as the delta function. So let's go take a look at this on some graphs and see what I'm talking about here. Okay, so here it is. I've actually just put in the formula for the normal distribution. And here it is. Here's the bump that I was talking about. And I can't write an epsilon in Desmos very easily, so I'm just using the letter E. And you can see as I adjust the parameter E, you can see how the bump gets taller and thinner, right? And it needs, as I said, if it gets thinner, it needs to get taller in order to retain an area of 1 under the curve. And as I let that E go to 0, it just kind of approaches that spike that I'm thinking about. So the Dirac delta is the limit as epsilon goes to 0. It's that spike. Okay? So we can also do some other things here. We can put in a parameter inside the function a t0 parameter. We're going to evaluate the function not at just t, but t minus t0. And what that does is it shifts the graph t0 units to the right. So if I adjust the t0 parameter, you can see that I can slide this bump around. And that's, in statistics, that's just the value of the mean where the distribution is centered. Okay? Now what I'm going to do here is I'm going to plot another function, a function that I just picked because I just felt like, hey, that's a cool function. And you can see it here graphed in green. And then what I'm going to do, and what you can see over here, is I'm going to evaluate the integral of that green function multiplied by my shifted bump. Okay? So I'm going to position this bump, let's position it back at 0 to start. And let's go ahead and integrate this from minus infinity to, how do I get an infinity in here? There we go. Okay, if I integrate this, and if I multiply them together and integrate them, look at the answer I get. I get 1.009. Okay? Now, if I evaluate the function at t0, in this case at 0, I get 1. Those values are pretty close. Now, as I make the bump narrower, as I decrease my epsilon, you'll see the value of the integral approaches the value of the function. Now, this is true no matter where I put this bump. If I shift the bump over here to 2, okay, the value of my function is 2.33333, repeating, 2 1/3. When I multiply the bump times the function and integrate it, I get something close to that. And as I make, again, the width of the bump narrower and narrower, we can see that these values approach the value of the function. So this is an important observation that we're making, that when we integrate, if we take an integral and we multiply the function times the bump, and we're actually going to take the limit as the epsilon goes to 0 and get the Dirac delta function. If I integrate this over any interval that contains t0, right? So our t0 will always be positive, so I can get away with just using the interval 0 to infinity. If our t0 is positive, that will contain t0. What we were seeing is that this is always just going to give us f evaluated at t0. And this is a very special feature of the Dirac delta function. When you multiply it by a function and integrate, you get the value of the function. So some things we can do with this. Well, we can look at its Laplace transform. Okay, if I take the Laplace transform of the Dirac delta, okay, what do I get? Well, I get the integral of e to the minus st times the Dirac delta, the shifted Dirac delta. And here I am, I'm multiplying something by Dirac delta, and so what does it do? It evaluates this function, which I'm viewing as a function of t here, at t0. And there we have the Laplace transform. Whatever t0 is, that'll be a number for us usually. That will be the number that goes here. So we can add this to our table of Laplace transforms, and we will put this to use. Let's look at how we can use it to solve a differential equation that involves an impulse. So let's look at a differential equation. And on the right-hand side, I have an impulse, just a shock. Imagine just all of a sudden at an instant in time, that time being t0, this shock was applied. What happens to this differential equation? We're going to imagine that a, b, and c are just constants. And we're also going to put some initial conditions on here. Let's say y of 0 and y prime of 0 are both 0. Okay? So to solve this, I'm going to take Laplace transforms. Well, if I take the Laplace transform of the left-hand side, when these are 0, it works out very nicely. I get the following thing. The right-hand side, we just computed that, becomes this. Solving for y, I'll factor out the y, divide by this stuff. We have this right here. Okay, well, what can we do with this? Well, we should recognize this. So think back from the previous videos that we had and what the inverse Laplace transform of this would be. Okay, so pause the video here, think about that. Okay, so you should have recognized that this thing, let's see if I can share my let's go to the table here. Should have found it in the table here if you didn't remember it. Here we go, this line right here. Right? I have e to the minus tau s, well, we have e to the minus t0s, same thing, times some function. The inverse Laplace transform is what we see on the left here. It is this expression involving a step function and our function, right? So this is what we're going to use. So there we go. So what we're saying is that the inverse Laplace transform of capital Y, that's lowercase y, is going to be the step function multiplied by the shift, the t0 shift of the inverse Laplace transform of this. So w of t is the inverse Laplace transform of that guy. Let me just express it like this. I'll just raise it to the -1 power instead of writing as a fraction just to save some space and some paper here. Okay? So this is how you solve this differential equation. Here, this is the solution. Okay? Now, couple things to make note of. All right? This omega here, this inverse Laplace transform of this function, happens to be the solution to the following differential equation. So here's some observations. It solves this differential equation with these initial conditions. Now you might say, well, wait a minute, this looks kind of like the differential equation we had, but keep in mind, this is the solution without the delta on the right-hand side. This is 0. And moreover, the solution that we got involved the shift of, I was calling it omega, I think it's really a W, I wanted it to be, to match what we have in our book. So I'll call it W from now on. The shift of W, all right? This is just W itself. W itself solves this differential equation. Okay. Now notice that it has initial conditions 0 at 0, but its derivative is 1 over a. And you can verify this on your own. That is a good exercise to verify this. Okay, so it is the solution to this differential equation. You can just verify this using Laplace transforms. Okay. On the other hand, we know how to solve this from long ago when we were talking about second-order linear differential equations. Right? We know that what we do to solve this is we look at the characteristic polynomial, and then we can very easily get the solutions that way. And the solutions depend on whether the roots of the characteristic polynomial are real, whether it's a repeated root, whether maybe they're complex roots. Right? So you get different kinds of solutions. So let's just say it this way. All right. Observation 1 was that this gives us the solution to this differential equation, but we know how to write down the solution to this differential equation by solving the characteristic polynomial, right? So we know how to find explicit solutions. So for example, in the case of a repeated root, we'd have something like we would have something like this would be our solution. Okay? So what we're really getting here is a shifted version of one of those as our solution. Okay? And how does that shift work? Well, if I were to draw a graph, what's going on here? Here we have the t-axis, right? What we have done is we've shifted this graph t units to the right. It's 0 up until we get there, and then the step function kicks in and allows this to exist past t0. So as soon as we get to t0, well, up to t0, we're 0, right? That's what the step function is forcing. It's forcing us to be 0 up to here. But then all of a sudden, this solution kicks in. Of course, it's the shift of that solution, shifted t0 units to the right, and so you would get something that maybe looks something like this. Right? So all of a sudden, you have this change in velocity. We were velocity 0, and then all of a sudden, wham, we have a positive velocity here. Okay, so one way we write that down is we say that the derivative at t0 approaching from the left, this is the limit of the derivatives from the left, is equal to 0. However, the derivative of our function at t0 approaching from the right is positive. In fact, it is equal to 1 over a in this situation. So the function itself is not differentiable at t0. It has two different derivatives depending on whether we're approaching from the right or the left. And there is no derivative exactly at this point. Okay, so let's look at an example of solving a differential equation with actual numbers in place and see what we get here. Okay, so what we'll do is we'll look at this guy. Okay, and I'll put in those nice initial conditions. Okay, well, what we have seen is that we know the solution is going to look like this. Right? Where this w function is the inverse Laplace transform of the reciprocal of, well, it comes from this, right? So if we just copy what we did before, it's going to be s squared plus 2s plus 1, the reciprocal of that. All right, well, if you look at this, this is the inverse Laplace transform of 1 over s plus 1 squared. And we can compute that inverse Laplace transform. That inverse Laplace transform is none other than just t to the e to the negative t. Okay? So another way to write down our solution would be, if I plug in t minus 3 in there in place of t, we could write it like this. Okay, or we could write it piecewise like this. It's equal to 0 until we get to 3. But then once we get up to 3, it all of a sudden takes on the value of this function here. So t minus 3 e to the negative t minus 3 for t greater than or equal to 3. Okay, so a way to write it down piecewise. And if we were to graph it here, we would see pretty much what we did before. When we get to 3, we were 0, and then all of a sudden it kicks up and then decays. And I forgot parentheses right there. Sorry about that. Right. So we have the 0 piece and the other piece kicking up. Okay? Now, one other thing I want to look at is how to treat situations where we have a function and a delta function at the same time. Okay? So let's take a look at this problem over here. I'm going to have a forcing function, which will be a nice continuous function, but then I'm going to add to it some impulse. Okay? All right. Well, how are we going to treat this? We have a sum of two things. Well, if you deal with something like this, you can use the principle of superposition. The principle of superposition tells you that you can treat these individual pieces separately if the differential equation is linear. And it's a linear differential equation, so I can do that, right? Basically, just to summarize this, view this as d of y, all right? It's some differential operator, they would call this in higher mathematics, and this is what it does to y. All right, so I'm just going to represent this as d of y. The principle of superposition says that if you happen to know that d of y1 equals some function f1, and d of y2 equals some function f2, then you can put these together, and you know that if y equals y1 plus y2, then d of y is f1 plus f2. In other words, we're running this backwards, right? We have a differential equation of this form where we have the sum of two functions, right? So what we're going to do is we're going to solve these two pieces individually. And then we know that by putting these two things together of the two pieces, we will have a solution to our differential equation. So we start with something like this, we piece it apart like this, break it up into the two different functions, solve them separately, and then piece together the solutions. This works when the differential equation is linear. Moreover, if you had initial conditions, say y1 of 0 equals a, and y2 of 0 equals b. Oh, let me not use a and b because I used a and b there. So let me use capital A and capital B. Okay. Then the initial condition that y will satisfy will be a plus b. Now I'm only doing the initial condition for y of 0, not y prime or y double prime or y triple prime, just to keep things simple, but that would work as well. All right. So this is the idea here. We're going to solve two separate differential equations, this one and then piece the solutions together by adding them. Okay. So So let's go ahead and do that with an example. Where did my example go? Okay, so here's our differential equation that I want to look at. And so we're going to use the principle of superposition to sort this out, okay? So we're going to first solve this differential equation. Now this is something we've talked about how to do a long time ago. This is something you can totally do. So work this out, pause the video, work it out on your own, and then see if you get the same answer as I do, okay? But what I'm going to do here is just give you the answer here. So just looking at that with these initial conditions, I'm going to call that y1. You should find that y1 is this function right here. This will satisfy these initial conditions at 0 and solve this differential equation. Okay? Now for y2, I'm going to solve this differential equation with the delta. Okay? So we know that y2 from our discussion up to this point is going to equal u of t minus 1 times w t minus 1 and I'm actually going to multiply it by 4. We know that, if that was a 1, we'd just get this, but if it's a 4, we'll multiply it by 4 here. What is W? W is the inverse Laplace transform of the polynomial that comes from here, the reciprocal of that polynomial. So it's going to be s squared plus 4. So 1 over s squared plus 4. Now, if you look this up on your table of Laplace transforms, you'll see that this corresponds to 1/2 of sine of 2t. Okay. Now remember, that's W. We want W t minus 1. So what we really need to do here is substitute t minus 1 in there, which gives me 2t minus 2. Of course, the 4 and the 1/2 will cancel each other out. Well, leave a 2 behind, right? And now we know our final solution is the sum of these two guys. So our solution is going to be this stuff plus this piece. Now you might be asking, why was I able to just put the initial conditions on this one, right? And remember, when we talked about the solution to this, we treated the initial conditions as if they were 0. Well, that all comes down to the principle of superposition that we were talking about. Since you add the initial conditions in the final result, you can just put the initial conditions on one of the two differential equations and take care of them there. And in this case, it only makes sense to actually put it on the differential equation that we did. I used the initial conditions on this one. When we dealt with the delta, we made sure to treat the case where the initial conditions were 0. So we left it that way. We left those initial conditions were 0 for that piece. And so we put all of the values, these initial conditions, on the differential equation that we solved for this piece. Okay? So now, let's just take a look at the graph of this guy down here and just see what's going on there. Okay? Okay, so here's the graph. You can see that we have one solution coming down this way until we get to about 1, and then you can see there's a sudden change. The solution's continuous, but it's not differentiably so, right? You can see that the velocity suddenly changes here. It's as if somebody whacked this thing as it was traveling through the air, and then its velocity changed, right? So you can see that little kink in the graph. And you can see the change in behavior there at t = 1, which is what we'd expect if there's an impulse force at time 1. All right, so that's it. Differential equations with impulses. I hope you learned something.